Good morning, students. This is Topic 7, Periodic Trends, Video A, Atomic Size. We just spent a month studying the basics of chemistry. I hope that you are beginning to see and feel some of its wonder. As a group of scholars, we are now ready to delve more deeply into understanding atoms. Let's start by looking at the observable trends in some of the properties of the elements. These trends are often called periodic trends, but we like to think of them as elemental trends. We will look at three: the size of atoms and ions, the ionization energy, and the electron affinity. Before we explore these trends, let's reacquaint ourselves with the periodic table and the language we will use in looking at the trends. Recall that the table is arranged in groups. These are the columns in the table. There are 18 groups. We also talk about the rows, which are called the periods. There are 7 periods, plus the 2 periods of the F-block elements. When we look at trends, we can explore how a physical property changes as we go across a period from left to right. That means we stay in a row and cross groups. The atomic number goes up. We can also go across a period from right to left. Here we are crossing the table in period 6. The atomic numbers are going down. When we use the word cross, we are going right to left or left to right. We can also go up and down a group. Here we go down group 2 and are crossing the periods from 1 to 7. When we go up a group, we start at period 7 and move to the top. The first periodic trend we will study is atomic size. If we continue to think of our atom as a sphere, then the natural measure is its radius. Specifically, we measure the bond length and then define the radius to be half the bond length. For bromine, the bond length is 228 picometers, and so the radius is 114 picometers. We can look at the atomic radii of all the atoms in the periodic table. We will exclude the transition metals and focus on the main group elements. As you move down a group, the atoms get bigger, and as you move across the period, the atoms get smaller. Here is a visual image that shows the trends in the radii of the main group elements in the periodic table. The measured radii are given in units of picometers. You might want to stop now and stare at this table. In your notebook, write down the trends you see in your own words. Let's now begin to understand why these trends occur. It is all about electrostatics as described by Coulomb's law. Here's the equation for Coulomb's law. Let's get a feel for how it works and what it means. Coulomb's law is about the force of attraction or repulsion between two charges. Q1 and Q2 refer to these two charges. Let's consider two positive charges. These charges repel and are pushed out. But what if we have one positive charge and one negative charge? These charges attract and are pulled in. Now what happens when the magnitude of the charges are not the same? Suppose we have 3 positive charges, but only 1 negative charge. The force is attractive and a lot stronger than the case when we had only 1 positive charge and 1 negative charge. Now how does all this relate to the size of the atom? Let's model the atom with the protons at the center of a circle. Put the electron on the circle. As the number of protons in the nucleus increases, the radius of the circle should decrease, because the attractive pull on the electron from the nucleus gets stronger. As you go across a period on the periodic table, you increase the number of protons, and so we would expect the size of the atom would decrease as we go across. This is exactly what happens, except the atomic radii don't decrease as much as expected. Let's not forget about the electrons. As we add electrons to the circle, each one is attracted to the nucleus but repelled by the other electrons. The actual size of the atom is a balance between the pull of the electrons into the nuclear center and the push of electrons away from each other. As we go across the period, the pull of the electrons into the nucleus is greater and the radius decreases. Okay, but what happens when we go to a new period? We see the same trend across each period. Atomic size decreases as you move across the period. But as we go down a group, the radius increases, even though the number of protons is also increasing. Why is this? As we go down a group, we increase the number of atomic energy levels that contain the electrons. Each shell is larger than the prior shell, and so the size of the atoms increases. So where are we? We can use the periodic table to predict atomic size. Atomic size increases as we go down a group because the number of shells increases. Atomic size decreases as we go across a period because the number of protons increases and shrinks the electronic cloud. Now let's practice. Use only a periodic table and your knowledge of trends to rank the 4 atoms from greatest to smallest. Pause the video here and write the answers in your notebook. Here's the solution. It is important to realize that all the atoms in period 4 are bigger than all the atoms in the earlier periods, so that potassium is the largest atom. Conversely, fluorine in period 2 is the smallest atom. Sulfur and chlorine are in the middle, and we order them by realizing that the size decreases as we go across a period from left to right. Good morning, students. This is topic 7, video B, ionic size. We have learned to use fundamental electrostatic arguments to rationalize atomic size. But what about ions? Can we use the same logic to estimate sizes of ions? After all, ions are nothing more than charged atoms. Consider the sodium atom and the sodium ion. Here are the electron configurations of the atom and the corresponding ion. Recall that the 2s and 2p electrons are in a single shell, shown in the figure as one concentric circle with 8 electrons. Notice that the ion has one fewer shell than the atom. We would predict then that the sodium ion would be smaller than the sodium atom, and we would be right. Cations are always smaller than the atoms they come from. What about anions? Let's consider the fluorine atom and the fluoride ion. Here are the electron configurations. The atom and ion have the same shells and the same positive nuclear charge, that is the same number of protons, so the only difference is the number of electrons. The anion has more electronic repulsions, so we would expect the fluoride ion to be larger than fluorine. Again, we would be right. Anions are always larger than the atoms they come from. Let's summarize by visualizing the sizes of some atoms and their ions. Cations are always smaller than the atoms they come from, and anions are always larger than the atoms they come from. Pause here and make sure you can explain all the trends you see in this table. Let's practice by thinking about a new idea. Isoelectronic ions and atoms have the same number of electrons. Pause the video here and convince yourself the statement is true by filling in the table shown below. Here are the solutions. All ions are isoelectronic. Notice that some atoms gain electrons and some lose electrons to create the isoelectronic ions that have the configuration of neon. Now try to arrange the isoelectronic species in order of decreasing radii, that is, from largest to smallest. Pause here and write the answer in your notebook. Here's the trend. Since the number of electrons are the same in each ion, the radius is determined by the number of protons, according to Coulomb's law. The nucleus of the ion with the greatest number of protons, that is the Al3+, has the largest pull on the electrons and is therefore the smallest ion. Sometimes, students think that because sodium, magnesium, and aluminum are in period 3, they should be bigger. But remember, these are isoelectronic because they have lost different numbers of electrons. Good morning, students. This is topic 7, video C, Ionization Energy, part 1. We continue our study of periodic trends. There are 2 we haven't looked at yet. Let's turn our attention to ionization energy. Ionization energy is the energy it takes to remove an electron from an atom. We can talk about the first ionization energy, the second ionization energy, and even the third ionization energy. Ionization energies have been measured and tabulated. Here is a table of ionization energies for the elements in period 3. Looking at the numbers, we can see that each successive ionization energy is larger than the last. I1 refers to the first ionization energy and is the energy it takes to remove the outermost electron from the atom. This electron is the easiest electron to remove. It takes more energy to remove the second electron, which is I2, and then more energy still to remove the third electron. The table continues onward with I4, I5, etc. This means that it is more difficult to remove successive electrons. When you remove electrons, the ion's radius decreases because there are fewer and fewer electron repulsions. To observe trends in ionization energy, let's plot the first ionization energy, that is I1, as a function of atomic number. We can do the same for the second ionization energy, and even the third ionization energy. Notice the large ionization energy in the I2 and I3 lines. To understand this, let's focus on the pink line. There is a big jump between I1 and I2 of sodium, and between I2 and I3 of magnesium. This pink line distinguishes the inner shell electrons, or core electrons, from the outer shell, or valence electrons. Remember that we are already familiar with this concept. The valence electrons are shown in the electron configurations, and the core electrons are represented by the inert gas. Core electrons are much more difficult to remove than valence electrons. Let's practice by looking at a typical exam question. Pause the video here and answer the question. Here's an explanation. Ponder this explanation and make sure it is clear. Let's take a moment to relate electron configurations, energy level diagrams, and ionization energies. Remember that an electron configuration shows all the orbitals that hold electrons for a given atom, and that each orbital has an energy that we can represent on an energy level diagram. For sodium, there are no electrons in the 3p, 3d, or 4s electrons. We're going to shrink the orbitals that matter and put a double slash in the energy axis to indicate that there is a big break between the energy of the 1s orbital and the energy of the 2s orbital. Now we draw a line that corresponds to the energy of the free electron on the energy scale and put the sodium electrons into the orbital energy level diagram. we are going to imagine pulling the electrons entirely out of the atom, one at a time. If we do this, the removed electron is no longer bound to the nucleus and can be visualized as sitting on the free line. The electron configuration of the sodium +1 ion is now 1s2, 2s2, 2p6. The first ionization energy is the energy it took to kick the 3s electron to the free line. Let's draw the energy level diagram for what is now the sodium +1 ion. Notice that the orbital energies are a little bit lower than they were when we had the sodium atom, and the 3s orbital is gone. Why would the orbital energies drop a bit? In sodium +1, we have one fewer electron, and therefore fewer electron-electron repulsions, and so the orbital energies get a little more attractive. Attractive energies are lower in energy. Let's remove the second electron from the 2p orbital and make the sodium 2+ ion. The second ionization energy is much greater than the first because we removed an electron from the second shell. This means that the second ionization energy is going to be larger than the first ionization energy. When we removed the second electron, we reduced electron-electron repulsions. Now let's remove the third electron to make a sodium 3+ ion. We see that I3 is once again larger than I2. The difference in ionization energy between I3 and I2 is not as large as the difference between I2 and I1, because this electron came from the same p shell as the second electron. And once again, the energy levels are reduced. This is a general principle. As we remove an electron one by one from an atom, the ionization energy gets larger because each successive electron is more tightly bound than the prior electron due to the reduction in repulsions. When the successive electron comes from a new shell, the ionization energy increases dramatically, as shown by the pink line. Good morning, students. This is topic 7, video D, Ionization Energy, part 2. We have learned how to understand the trends in successive ionization energies in atoms. Now let's look at the first ionization energy as we go across a period. Although the arrow is pointing down, these atoms are increasing across period 3. We know that atoms get smaller as we move across a period, and so ionization energy increases. This is what we would expect based on the same electrostatic argument we had for size. You will notice that there are some exceptions to this general trend. Why is the ionization energy for aluminum smaller than the ionization energy for magnesium? Let's go back to the electron configurations to answer this question. The electron configuration for magnesium has 2 paired electrons in the 3s orbital. The aluminum configuration puts an electron in the 3p orbital. The 3p is typically slightly higher in energy than the 3s, and so it is easier to remove a 3p electron than a 3s electron. The electrons in the 3p orbitals are said to be shielded by the 3s electrons. Shielded electrons are less strongly attracted to the nucleus. What about the second exception? Why is the ionization energy for sulfur smaller than that for phosphorus? The electron configuration of phosphorus shows 3p electrons with the same spin in different p orbitals. The electron configuration for sulfur shows that 2 of the p electrons have their spins paired. Remember that it takes energy to pair electrons. We learned this when we studied electron configurations. So the sulfur p electrons are actually at a higher energy than the corresponding phosphorus electrons. This makes it easier to remove them. Let's practice interpreting ionization energies and relating them to energy level diagrams. Match the diagrams to P or S and then load electrons into their energy levels. Pause the video here and in your notebook show how the sulfur ionization energy would be smaller than the phosphorus ionization energy. Here is the solution. Sulfur has a slightly smaller ionization energy due to the increase in electron-electron repulsions that cause the 3p orbital energies to be higher than expected. So where are we? In general, ionization energy decreases as the size of the atom or ion increases. So ionization energy decreases as we go down a group and generally increases as you move across a period. There are two notable exceptions. The electron-electron repulsions in the fourth p electron as you go from group 15 to group 16 makes these electrons easier to remove. And the shielding of the p electrons in group 13 by their s electrons make the first p electrons easier to remove. Now let's practice by looking at an ionization energy graph for all the elements and see the trends. Pause the video here, maybe even print out the graph and identify the trends in your notebook. Here are the trends. First, group 1. It is a little difficult to see, but the ionization energies are generally decreasing. What about period 2? In general, the ionization energy is increasing as the atomic number increases. Now here's an exception that involves shielding. We are showing the beryllium to boron exception, but you might have identified the equivalent exception in period 3, shown by the purple line. An exception that involves electron pairing in period 2 is shown here. Good morning, students. This is topic 7, video E, electron affinity. We have one more trend to consider, electron affinity. In the chemical literature, electron affinity has been defined a couple of different ways. We will choose to define electron affinity as the heat released when a gaseous atom gains an electron to create a negative ion. This is the definition Linus Pauling used in his famous book, The Nature of the Chemical Bond. Linus Pauling is perhaps the most famous chemist of the 20th century. He won not one, but 2 Nobel Prizes in chemistry and in peace. So let's use his definition. The chemical equation corresponding to this definition of the electron affinity is shown symbolically here. For chlorine and oxygen, the delta H of the reaction is negative, telling us that energy is given off. We define the electron affinity as minus the delta H. This means that the more negative the delta H value, the more heat is released, and the larger the electron affinity. This means the ion is more stable than the atom. Electron affinity values are tabulated. Let's look at chlorine to be sure we can interpret electron affinities. When an electron binds to a chlorine atom, energy is released and the electron affinity is positive. We see that chlorine has the largest number on the table, so we say that chlorine has the greatest electron affinity. The electron affinity is a measure of the energy released. When the chlorine ion is formed, 349 kilojoules per mole of energy are released. This is a favorable process, and the chloride ion is stable compared to the isolated chlorine atom. In fact, all of the group 17 atoms exhibit favorable electron affinities. These are called halogens. In general, electron affinity decreases as you go down a group, and is consistent with the trends observed in ionization energy and atomic size. We can explain the trend by looking at electron configurations. For each of the halogens, the electron configuration shows a p5 valence shell, they all readily accept one more electron. As you go down group 17, the elements get bigger. The electron added is further from the nucleus, and so the attraction to the nucleus is weaker. We could also say that the binding energy of the electron is lower. Let's return to the electron affinity table. While in general, the electron affinities get smaller as you go down a group, there are some clear exceptions. The atoms in the P block of period 2 have electron affinities that are somewhat lower than the atoms in period 3. This is probably because the period 2 atoms are extremely small, and the electron-electron repulsions are greater than in period 3. Notice that the metals have significantly lower electron affinities than the halogens. Also notice that the noble gases and a few other elements have no electron affinities listed. The formation of an anion from these elements is not favorable. You don't need to memorize the numbers in the electron affinity table. You should, however, recognize that atoms with positive electron affinities form stable anions, and you should be able to use an electron affinity table that is given to you. Now let's practice a multiple choice question. Pause the video here and take this opportunity to synthesize your knowledge on periodic trends. Write the answer in your notebook. The answer is A. Try writing a couple of other questions that vary these relationships. Writing things down is an important part of the learning process. Hopefully your notebook is your own, is creative, and could even be a work of art.